Hi, my name is Dr. Luke Nakiri. I'm an assistant professor in marine engineering technology. I do teach mechanics of materials and marine construction materials. So this lab is materials lab, and we do process materials to look at the strength and property of different materials, mostly steel. Currently we have 4 or 5 experiments that are ongoing, and students will actually be explaining the specifics of the experiments that they are doing. So briefly, we have a group of students who are doing a tensile test, which is an experiment that is used to determine the mechanical properties, different mechanical properties of materials, mostly tensile strength, yield strength of materials, and the toughness, etc. So there's also another group of students who are doing the metallographic and polishing of stainless steel samples and brass to expose the microstructure of the materials that we are looking at and correlate those grain structures with the mechanical properties. So that will involve using the Numaski Optical Microscope, which you'll see just in a little bit, and we're going to use the Rockwell hardness test to probe the hardness of the same materials that we do polish. There's also another group that are doing the crystallography, looking at the unit, atomic unit cell of the various structures, metallic structures, polymeric structures. So this is a Numaski optical microscope. We do use it to look at the surface morphology of metals that has been mechanically polished to expose basically the grains within the metal. Mostly the samples we do, we treat them at different temperatures and then anneal them, temper them, etc. And that way we basically alter the mechanical strength of those materials, and the strength of these materials are directly related to the size of the grain, and that's what Mina is doing here. So you can tell her what you're doing, what you've done?
Yeah, so basically after polishing this one is quenched steel, so that means we brought it up to a temperature of 850 degrees, and then we cooled it down in some water. So what it does is it quenches the steel and changes the properties of it a little, and then you polish it starting off with 120 grit all the way up to 1200 grit, and once you polish it you should get like a mirror-like surface. And then we put it under the microscope at different magnifications, so that way we can see the grain size, and that way we can check to make sure that there's no imperfections or scratches.
Howdy, we're going to make a crystal structure. And it's made, we're making it out of balls. And right now we're doing a BCC, which is a body center cubic, and then later an FCC, which is a face center cubic. Using these little balls to fill the spaces of the crystal structure that we have. So like these little tiny structures within it.
Howdy, future engineers. My name is Noah Trio, cadet, marine engineer, and I'm a junior in Texas A&M at Galveston. Today, in this materials class, we are handling a piece of material that we have created in a lab that took us about 3 hours to make. So what we have here behind me is a tension machine, and what it does, it basically presses this piece of material right here, as you can see, to break at this point right here. and sometimes it stretches or presses, whatever you want. Hello, once again, I'm here to show you how this machine works. So what you do here, you screw in your piece of metal. Well, and this was one piece. Let me show you another piece of material here. So once look like this, screw it in right here, like so. Then you'll get the machine to go up and down to where it'll screw in place. Then you start the machine, and displayed right here will show you your pounds per force that is being applied to it, and the percentage of, what was it called? Elongation. And once you get that, you will then take it to this computer, as I'll show you right now. Howdy, future engineers. As you can see here, I can show you that after operation, once the material snapped, as I have shown you guys, we can see it displayed here of how much force is being applied to the material and where it snapped. As you can see, it goes straight up along the stress KSI, and as it increases in strain inch per inch. And I'll get back to you guys and we'll show you how it operates.
You can see it a little bit getting ready.
How can you tell?
Because this number is dropping very fast.
Howdy, future engineers. Now I'm going to pull out my material out of the oven that we have heat treated at 800 degrees Celsius. It's very hot. Look at that. And we'll just let it cool down for a couple minutes.
Alright, so right here we have our pieces of metal that we've tested in this tensile machine. We basically concluded that the heat-treated steel has the most hardness but the less ductility, and the aluminum had the most ductility. It was able to stretch the most in the machine. But when the steel wasn't heat-treated, it actually had less hardness and more ductility. So we can conclude that heat treating the metals gives it more strength, but it will definitely break it apart without stretching it out, basically.